טוב. אז, אם ירצה השם, אנחנו באוניברסיטת בר אילן, אז מאוד חשוב. אנחנו נעשה היום קוונטיזציה של השדה האלקטרומגנטי. או לפחות נתחיל. אבל, again, I'm speaking in Hebrew. Switch. Although, yeah. So, well, okay. So, our subjects today are classical coherence. Well, we discussed last time, at least intuitively, the concept of what I would call first-order coherence, and specifically in time. Now we'll see that it works also in space. So we can talk about, we'll have terms like coherence time and coherence length. Now you should be careful about length. It could also be width. I'll explain what do we... Those two, length and time, could sometimes be interchanged because with the speed of light, every length is time. But when we talk about the coherence width, so this is something that is not the same. This has to do with what we call temporal coherence. And this one has to do with spatial coherence. So I'll remind you about those soon. And there is the general form of, but both of those relate to what we call first order coherence. And if we talk about first order coherence, there's probably also higher orders of coherence. So the other order that we'll talk about is, we'll talk also about second order. Now here, and we'll stop. I mean, we'll discuss the concept and what does it mean to have higher orders of coherence. And it has a meaning. It's not, it is of value. But in terms of what we will discuss is, so here, there's of course further to the nth order. Well, now you heard me, nth order. So this we only define, but we won't do anything about. Here we'll mention an important effect, which is the Hanbury, Brown, and Twiss. Now, this is a little bit misleading because, as I told you before, Hanbury, Brown, and Twiss are two people. One is named Hanbury Brown. The other one is Twiss. They did an experiment. People call the Hanbury, Brown, and Twiss experiment and second order coherence and intensity correlations, all of those are interchanged terms. You'll hear them all the time. What I want you to understand, so this has to do with intensity coherence or correlation. Anyway, this is an experiment that has to do with the intensity of the light. And it discusses the coherence, and again, we'll define what we mean by coherence very soon. But this has also this is an experiment that was done in 1956. This is an experiment in radio astronomy, where two experimentalists wanted to measure the size of a star, of a nearby star. There's a very bright star in the southern sky. Maybe it has to do with the fact that Twiss was an Australian. By the way, if you look for the name of Henry Brown, you'll find a lot of his work. There's a lot published. He did a lot of things, and there's many papers written by him. But Twiss apparently have done only this and didn't do anything else. Maybe, and some say that it is because he was somehow related, that most of his work was in some secret agency of some country. So I don't know. Maybe it's true. But as I told you, this is an experiment in which two physicists of radio astronomy, basically engineers, wanted to measure the size or the angular size. You know, if you look at the sun or the moon, you can measure their angular width. Both of them are about half a degree wide. Why is that? Because they're close enough so that we can, although they are, although they're far away from us, 300,000 kilometers or 150 million kilometers, still their width, their spatial width is wide enough so that we can actually observe their size and see it. But when you go to stars, it's no longer the case. Stars look like a point. It has to do with the size of the microscope you're using, or the aperture that you're using in order to see them, because it cannot, you've heard now that there was work about watching, it's what they call the horizon telescope. There's a word before that, event horizon telescope, that recently was able to observe a black hole. They were able to observe a black hole in frequency, in radio frequency, in the radio range, by making the entire Earth a huge antenna. Now, of course, you cannot have one antenna that is the size of the entire Earth. But you could have several. The more you have, then it's better. Telescopes, radio telescopes in different locations of the world, and somehow maybe you can coherently combine them in order to make one huge antenna. Well, it won't be huge, but it will have components. And since the Earth rotates, then they also move those antennas. So you can, by this, with a lot of amazing algorithms, you can construct, you can resolve, and this is something that most of you, I think, learned some form of optics, and you know that you need a large aperture in order to see small things. So the numerical aperture, if you want to resolve things that are very close apart. So now the problem was that they didn't have such a large telescope, and they didn't have perfect timing or the ability to coherently combine signals from different antennas, and they still wanted to measure the angular width of a star that was far away, and that a single telescope that they had at the time could not resolve or could not see the difference between that star and just a point source. There was no way to tell. We'll discuss this more in more detail soon. So they figured out a way to do this with simple telescopes. 2 simple telescopes, and without with not crazily, with the available electronics that they had at the time that could not do perfect time correlation between the two. We'll discuss this. But so they figured a nice way, and they were very happy about it, and they published it. And the fact that they could measure the angular width of a star that is about 8 light years away, that was sufficient to put their paper in Nature. And then suddenly some quantum physicists made some calculation and realized that the intensity of the light that they were observing was so weak that they could not observe more than 1 photon at a time. So actually this whole experiment sparked the understanding of what on earth does it mean to have a photon. So they were trying to look at the Hunbury-Brown and Twiss experiment, which Hunbury-Brown and Twiss analyzed classically completely. They didn't, and they looked at it. This was, I don't know, experiment in radio. We have a field, we have an intensity, we have, and then they said, no, this can't be happening. Something is wrong with this experiment, because it cannot happen that those 2 detectors that are at different locations. I mean, how are we talking about intensity correlations when none of the detectors even detected at the same time? The intensity was so weak that the probability that you could see a photon here and there at the same time was very small. So the quantum understanding of the Hunbury-Brown and Twiss was actually the birth of quantum optics. Because shortly after the experiment, there was a lot of debate and people who were saying this is nonsense, what they're doing is impossible because quantum mechanics doesn't allow it. And then Roy Glauber in the early 60s did a complete quantum analysis of coherence. What he published, what he got the Nobel Prize for, I don't remember if it was 2006, but about, thank you. I was close. So Roy Glauber received the Nobel Prize for completing the theory of coherence in a quantum way. Now, and he resolved the problem, and he showed that everything is fine with the Hunbury-Brown and Twiss experiment, and the problem is with those who know too much quantum physics and don't remember classical physics at all. So this is why we first learn classical coherence. So, yeah, and then, but actually Hunbury-Brown and Twiss and the intensity coherence is just one case of many possibilities of coherence, and actually the higher you go in the order, the zoo of possibilities becomes higher and higher, wider and wider. There's more possibilities. So we'll mention just 2 of them. So now, as I told you last time, I never know the field exactly. I mean, I have a source and it emits a field, but I don't know it. If you remember, it's like the wave function. I don't know the wave function, I can know the density matrix. Basically, the density matrix and the coherence are just exactly the same. Because, you know, I told you I cannot know psi of x, but I can know this. Of course, this can be measured. And another thing that could be measured is like things like the correlation between, I don't know, maybe something like that. On average. Why can this be measured? Well, this is, okay. This is in the space basis. The coherence between, so, you know, what we discussed before was writing things like, if I have a state which is in a two-level system, all we had was two levels. So we had just two coefficients. And then we said that, look, I can measure C1, I can measure C2, absolute value squared, and I can maybe measure the coherence function. But in this case, we're working in the basis of ground and excited, and there are only two states in there, and this is all there is. Of course, if we are working in a state where we have sum of Ci, I don't know, state I, then we'll have a coherence matrix. Now I'm calling it a coherence matrix. Before we called it a density matrix. And I'm sorry for not making my phone quiet. No, I can't speak, and I'll try to make sure that you don't ring again. And in this case, we were thinking of, you know, that was, like, this is the state psi, it equals this. Then we'll have a matrix. We are on the diagonal, we have C1 absolute value squared, Cn absolute value squared. And the off-diagonal terms, which are Ci, Cj star. And here on the other side, there's Ci star, Cj, so on. So those are all the on-diagonal terms of the coherence matrix are the probabilities of having each state in the basis. And the off-diagonal terms are the coherence between them, coherences between them. We called it the coherence term. And we mentioned that we can measure only this. And actually, the fact that those are non-zero is what makes things interesting. It's what makes these U and V exist at all. And the Rabi fluctuations, the Rabi oscillation, all the coherent quantum physics exists only as long as these guys are non-zero. And we even discussed phenomenologically the possibility of losing this coherence due to decoherence processes. What are those decoherence processes? Things that cause us to lose knowledge, either because we don't know the Hamiltonian, or because, you know, we don't know of the Hamiltonian of different atoms, because different atoms have different locations and they behave differently, or because the Hamiltonians of all atoms is not exactly what we think. So this coherence is our problem, at least the way we described it so far. It's only a problem of our ability to know the exact dynamics of each atom. That is true. So coherence is related to knowledge and to order and to entropy. Now, but let's go back. So, of course, so that was coherence we discussed. the density matrix in the case of just 2 levels. Of course, it can be generalized to more, to the situations where there are more bases. And we could even discuss the case where the basis is continuous. We know of continuous bases, for example, position and momentum. So, you know, I can write the function, the wave function psi of x, as an expansion of this form using a delta function. So an integral of psi of x prime, delta of x minus x prime, dx prime. And this is Cx, coefficient. And this is the vector. Sorry, this is Cx prime. And you can see that this is basically nothing but sum over the coefficients of the probabilities of having the state. Of course, this is not a sum. This is a continuous expansion. And again, here, if we said that this is the probability of finding the particle in state number 1, then psi of x tag absolute value squared, this is the probability of finding it at x prime. And now we can talk about the question of, suppose that I know. What does this mean? What does this tell me? If you know something about C1, does this tell you something about C2? Is there a correlation between them? So, and the same thing would be here. We can ask ourselves, okay, so if I know something about psi at x, do I know something at some other point? X, let's call this x1, and let's call this, that's what I wrote before. Now, at least, all I'm telling you right now is that I've tried to make a connection between the density matrix in 2 levels that we did to an n-level density matrix that we didn't do anything about, to a continuous case. In all cases, it's the same. But what I want to show you is that we already met this kind of creatures, which are the correlation between the coefficients of 2 bases. Now I want to take this into the electric field. Now, and honestly, I don't know if you've taken already advanced quantum mechanics or not. Did you?
No.
No.
Yes.
Some have. No. One has, and some didn't. So in advanced quantum mechanics, you learn about second quantization. And second quantization in relation to standard quantum mechanics. It's a funny concept. What I want to tell you is that in second quantization, you quantize a field, a Schrödinger field. Interesting. Makes a headache. Now, but let me try to make some relation between the two. So what I want to say is that the standard quantum mechanics that you learned in Quantum Mechanics 1 in your undergraduate, is what we call first quantization. And it is analogous to classical electromagnetics. And then you can in electromagnetic, and I want to say is that there is a relation, a one-to-one relation between psi of x and the classical field E of x, and maybe t, of course. Now, if you want, I can tell you immediately where does it come from. I mean, this function, that depends on x and time, we have a wave equation for it, right? So we have, for this, we have the Schrödinger equation. For this one, we also have in one dimension at least.
That big though.
Yes, you're right. You reminded me. Okay. Is it better? So, and you know, even here, it's almost the same equation, right? I mean, there's v of x times psi in the x plus or minus. So the equations are similar. You can see. So this is the wave equation of the Schrödinger field, which has a wave amplitude, which is psi. And it's inconvenient because, I mean, it has some complicated meaning about probability, but still there is a wave amplitude, psi, as a function of x and t, and it goes according to a wave equation. And when we talk about the electric field, there's the wave equation. It's a different field. It doesn't have the same correlations, but still the questions about, you know, the solutions are not that different, especially if we have no potential. And by the way, here we could also have a potential. I mean, there is a very strong relation between the two equations, and you've seen that many times. Well, definitely the time-independent Schrödinger equation and the time-independent wave equation, which is called the Helmholtz equation, are basically the same equation. I mean, they're really exactly the same. Because the only difference here is in the time dependence. Once you separate out the time, the solutions are basically the same. And you could have situations, you know, for a wave equation when there is also an index of refraction that depends on space, then this is exactly like a potential in quantum mechanics. I don't know if you know, but the solution of the modes, the spatial modes of a laser in a waveguide, like in a fiber, are exactly the Hermite-Gauss modes of the harmonic oscillator. It's the same thing. So we can talk about psi as being a field, a Schrödinger field, just as we can talk about E as being an electrical field. And so now we want to look at the electric field. And by the way, for the electric field, we also have the same problem that we had for psi, which is we don't know it. We can't know the electric field. Now, for the electric field, we feel more convenient about it because conceptually, we could know it. We think there is an electric field anywhere in space. It's not a probabilistic thing. There's no wave function collapse and things like this. There's only a wave. But still, I mean, that's true. There's only there's a classical field, nothing collapses. There's a field here, and it oscillates in time, and it also propagates in space. So we'll see, I don't know, a sine wave in space, and this sine wave is moving in time, which means that every point is going up and down. Those are solutions of this equation, just as they are solution of this one. The problem is, well, here you have all kinds of problems, conceptual problems about the exact I don't know, interpretation of what the wave function is, and there's all this probability mumbo jumbo, all the things that makes quantum mechanics looks crazy. But in here, it's simple. It's just, it's moving too fast. It's oscillating at a frequency that I cannot measure. So I just don't know. I can't, this field is moving at the speed of light. This distance between waves is about 1 micron, if we're talking about in optics, and I cannot see it. It's just moving too fast, and it's smearing out, and there's no way I'll know this. And this is, so the problem is a problem of measurement. I cannot measure this directly. As we said before, in radio frequency, we can. In radio frequency, those waves are far enough apart. And if they have a distance of at least several meters, and the frequency is sufficiently low, then I do have detectors that can follow the fact that it's going up and down and up and down. But that has to do with the fact that, okay, this wave is slow enough. But when we go to, I don't know, above a terahertz or so, that's as far as our detectors go, then we lose this. We don't know. So there was a question. Yeah. Yes?
It's connected to the same problem that we can't measure the phase?
Yes. It's exactly that. Because I cannot freeze the wave, I cannot measure fast enough to just freeze the wave, then I don't know the phase at any time. To say the phase is to ask when is the wave exactly, where is 0? So, we don't know, but then, so that means that I cannot, I don't know. I mean, if I try to, this function, e of x and t, I don't know it. And I don't have a way to measure it. But I do have a way to measure correlations. So now the problem, then it comes back to here. We said, look, I don't know the wave function. It's not a measurable quantity. But there are measurable quantities which are probabilities and coherences. Now in quantum mechanics, this has to do with the concept of why the wave function cannot be measured, and it's very philosophical. But here, there is a very direct answer. You cannot measure the field because it's changing too fast. And therefore, so I cannot, but I definitely can measure this. Well, not exactly. What we measure is this averaged, which means, you know, if we think for a moment about E of x and t as being, I don't know, sine of kx minus omega t, let's take a plane wave solution, then clearly this with some amplitude. This absolute value squared is this a squared times sine squared. And I could even say, okay, but you know, a sine squared, so this is a squared times what? Times half. I think plus or minus, it doesn't really matter. I think minus 1/2 cosine twice omega t. Now, you can check, but that's not the point. There is this thing, if I look, the true instantaneous intensity, truly instantaneous intensity is fluctuating in time. It is, you know, sometimes it can have a maximum of a squared, can have a minimum of 0. Of course, it's a sine wave. You took the intensity of a sine wave. So it's just that, you know, it looks like this. So this is, but this is not, but then, of course, as we said, this is too fast to observe. I have a detector that measures the intensity, and its averaging time is always sufficiently long that this is completely washed out. So when we talk about the average of this, this is just a squared. And if, you know, and as we mentioned already several times, we can talk here about the complex. So if I think of the wave as being a complex field, A, which is now a complex number, e to the I omega t plus complex conjugate, then what we measure, so this is a squared, or even the average of a squared over the integration time. This guy is completely gone. There's no way to measure that one. And in this case, so what we can measure is the intensity, which is this, amplitude squared. So, yeah. And about the half, well, forget it. I could have put a 2 here to begin with. So that's one thing I can measure. And as I told you before, it's not the only thing I can measure. So I put a detector that responds not to the amplitude of oscillation, but to how strong it is. Whether at some place is the wave, you know, is the sea, is there a storm, or is it a quiet day? So this is what you can tell the difference from. And the question, and as I showed you before, an interference experiment measures not just the intensity, the local intensity in time and at the same time, or maybe at the same place. Of course, I can talk about this, E of x and t. Okay, this. And this function a is also, it's a function of x. It could be varying as a function of time, as we mentioned. This is what we measure. And this is averaged over the detection time. That can be one situation where you really have a detector that has some averaging time. So it will detect the slow variations of the intensity. But if the intensity has also fast variations, maybe faster than its own integration time, it won't be able to detect it. But forget about this for a moment. This is a problem of the detector, right? Take a faster detector. Take a better detector. An intensity detector, okay? But get a better one. There's another thing that would happen, and that has to do with the fact that maybe there is some randomness that you don't control. Maybe, for example, there is, you know, I try to measure, I put my detector in front of this lamp. I'll see an intensity that is fluctuating in time. Why? Because the lamp itself generates fluctuating, random, unpredicted electric field. And then I can only discuss. So, and now the problem is a problem of knowledge. I don't know exactly what is happening in the lamp. So I can only discuss it because it's random and too detailed. So I can only discuss it in a statistical kind of manner. I can talk about, well, suppose that, you know, I measure the field now. What will I know in some time later? And now it becomes an ensemble average. I try to say something about the statistics of the possible outcomes of the lamp. So we can talk about this for a detection time, or I can talk about it in the ensemble of possible functions. In this case, intensities. It doesn't have to be intensities, or let's scenarios. And that is something that is important to understand. So, now, I always have big plans at the beginning of the lecture, and now I'm not sure whether we will actually quantize the field today, but we will do some interesting stuff. Okay, so as I told you, now suppose here that I have, so let's think about, I have here some source of light, and on purpose I don't know how it looks, so I'll draw a lamp that emits light. In all directions. Well, it's a, you know, it's a, yeah. And now, well, what I'll do is, suppose now that I'll put it in front of an interferometer. So I'll split the light coming out of here into two directions, and then meet them on a beam splitter. So this is a beam splitter. It could be a 50-50 beam splitter. It doesn't have to be. But let's think about this. And this could be another 50-50 beam splitter. And here there is a delay tau. And as we said, what we can do now is to measure, I don't know, either this intensity. So here there's going to be I1, and there's I2. And this is what these two are measuring. Sorry, we'll put here something different. I can even take the difference between those two detectors. In a moment, you'll see why. So what do we have here? This has some field, E of t. I don't know what it is. No idea. So here, okay, of course, there is a delay here, but let's disregard the common delay across the system, and tau is just the time difference between those two. So here there is those two copies of 1 over square root of 2 if you wish. E of t, and the same here, 1 over square root of 2 e of t. Why not? And now I'm discussing only the time. This is what we did before. And then if I ask myself what comes here, so here is, of course, there is a delay here, but we took that to be 0. And here there's the same thing, but just delayed. And what a beam splitter does is it generates the sum and difference. So if I ask myself what is happening here, let's make this a bit longer so that we can write here. Here we'll have half of E of t plus E of t plus tau. And this is what will come to the detector. And here we'll have the same thing, but with a minus sign. Why minus? Because energy must be conserved. If you have constructive interference in one side, there must be a destructive interference in the other one. Otherwise, energy is somehow being born. A beam splitter must be energy preserving. We'll discuss this pretty soon as well. So here there is the same thing, E of t minus E of t plus tau. And now we're taking the intensity of that, the intensity of this, and the difference. Well, and you can see that if I take the intensity here, I'll see the interference term. And as we mentioned before, so what we will see is, well, yeah. I don't want to carry with me all those halves and things. So we will have this E of t squared plus E of t plus tau, absolute value squared, plus or minus twice the real part of E of t, E star of t plus tau. And when we take the difference between those two, all we will have here is just the real part of E of t, E star of t plus tau. This is, as we said, a complex function. And this is, so an interference experiment, this is the existence of this term is what will generate an interference to begin with. That is the source. And then we need to know that actually what we measure, we observe this. So first of all, we average this over the detection time of the detector. So whatever happens faster than what the detector can do, we just don't see. So if, for example, if this is fluctuating too fast for the detector to observe, then we don't see it at all. And then there are the statistical properties of this term. I can talk now. I put this in front of an unknown source whose field as a function of time is not something I know, and not just because it's a sine wave that I don't know its phase. It has I don't know, its frequencies could be anything. Its phase could fluctuate in time and in space. Its intensity could fluctuate in time and in space, and I don't know. There's a source here that I have no idea what and where will the intensity or the phase be. The only thing that I can tell is if I can talk about averages or correlations, or relations between one time to another or one point in space to another. So now, so we define the coherence function. So this is gamma of t as a function of time. This is defined to be this. Average over the ensemble of possible outcomes, and if you want, you can include the detector in there. So including the detection limitations. Now, of course, and now this is, so this, and this is something that we did last time, and we realized. So we can see that by definition, gamma is defined as the correlation between the field at time t to the field at time at a later time t tau. So this is the autocorrelation of the field. And then if this is, now we can say the word, if this is a stationary field where the ensemble average is the same as a temporal average. So if, so in the case of a stationary oh, you've heard the name ergodic in statistical mechanics. If we assume a stationary situation, then this is like 1 over t, or at least the limit of t goes to infinity of 1 over t, integral of t from t0 to t0 plus t, e of t, e star of t plus tau. Oh, I'm sorry. This is not necessarily, okay. So, okay, I'm sorry. Normally, this could be a function of both t and tau. The time difference is important. But if this is stationary, then this can be written as a temporal average, and then it depends only on tau. And then that means that assuming a stationary or ergodic source, most sources are, except sources that emit very short pulses. But a source like this is definitely, it doesn't matter whether I measure it now or an hour later or even a minute later, the probability of having some kind of field is stationary in time. It doesn't matter when I turned on the light. So this gamma is just the autocorrelation of the field. And from that we have the Wiener-Khinchin theorem, which just tells us that in frequency, whoa, it seems okay, equals to just that. This is just a Fourier relation. This is called the Wiener-Khinchin theorem. But what does it tell you? It tells you that if you measure, let's put a tilde here for it, Fourier transform. What it tells you is that if you measure the field, there is a strong relation with the coherence time. This coherence function, well, you know, this is an autocorrelation. An autocorrelation has a maximum at 0. Autocorrelation is always 1 at 0 delay. So let's see. What does it look like? What? Say again? Gamma of tau.
No, I mean in the integration of the correlation. It's not supposed to be d tau?
No.
Because you're moving the signal to d tau.
No. I'm not moving in tau. I'm saying that, well, actually they are both symmetric, but the integration is dt. Why? Well, that's the point. I'm looking at the, I was talking about the ensemble average. But if this is a stationary, what I'm saying, let's assume, I don't know what this lamp is emitting, but there is a probability that it will emit this plane wave, and there's a probability that it will emit that plane wave. Let's take only 2 of them for a moment, okay? So now, okay. So what is the ensemble average of this coherence function? Well, I don't know, but I can say, okay, but suppose that now I just stay and look at the lamp for a long enough time. Then it will have sometimes it will generate this one, sometimes it will generate this one. And if the probability of having each one is stationary in time, then I can just look at the time average. The time average for a long enough time will give me all the possibilities. It will average over all the possibilities because the lamp will visit all those probabilities, all those possibilities with the relevant probability which does not change over time. And in this case, and this is why this ensemble average, which basically depends on both times, now is independent of the specific time because, as I said, the lamp doesn't know what time it is. It just operates the same at every time. Or you could say that there is what we say translational invariance. You can shift the origin of time or shift the origin of space, and the properties of this don't change. Now, as I said before, this gamma of tau equals 0. This one is just an integral from minus infinity to plus infinity at this limit of and this is just the total energy. And this is the maximum. So always gamma of t, that's the, I don't know, how do we, give me a letter for energy. U, total energy. And so gamma as a function of tau must be the best it can be is a constant. That's the maximum. At 0, it has a maximum. The best it can be is a constant, and usually it just decays. What I just plotted here, it has to be symmetric, by the way. And this is what I plotted here is gamma of tau, absolute value squared as a function of tau. Now, so it will have a width here. We can call it the coherence time. Usually we measure from 0, so actually I should probably do just. And that's the maximum delay you can have, and that has to do with how long does this, the fact that you know the field here, how long does it tell you what it will be later? And as from the Wiener-Khinchinna theorem, this is directly related. So this is just the width of the autocorrelation, which is Fourier related to the width of the Fourier spectrum. So the correlation time is by 1 over delta omega. 1, 2 pi, that's not, if I write delta omega, it should be 2 pi. If I don't write, let's put it, new frequency, so, and ni is omega over 2 pi. So indeed, for example, we can ask ourselves, suppose that we have a perfect sine wave. How does its coherence function look? Suppose that I really have a field. Suppose that I know the field and that E of x and t, you know what, just E of t, equals a e to the I omega t. Then, okay, then gamma of tau equals what? Integral of minus infinity to plus infinity dt what? A squared times e to the I omega t times e to the minus I omega t plus tau. And this is e to the minus I omega tau. And then we'll have, so this equals e to the minus I omega tau times integral times a bar ribua a squared integral dt. Well, that doesn't matter. Eventually, of course, the energy of a plane wave is infinite. So the fact that this explodes, that's not the point. But the point is that, sorry, not t, tau. And indeed, the intensity of gamma of tau is just a, well, there was a squared here, so it's going to be a to the fourth, but it's a constant. So for a perfectly coherent sine wave, if I have just a perfectly coherent sine wave that doesn't change, it would look like this. Perfect single frequency, which has and if your laser is not perfect, at some point it will decay. If it's a lamp like this, it will decay very fast because its frequency is very undefined. There's a very large uncertainty in the frequency. It emits over a band which is about 100 terahertz wide, actually even more. Now let's think about this. This emits over the entire visible range. The visible range is between 400 nanometers and 700 nanometers. Okay, frequencies. 1 micron is 300 nanometers, 300 terahertz. Okay, so half a micron is 600 terahertz. Now we have the span between 0.4 micron to 0.7 micron. Believe me, you'll have a span of about 300 terahertz. So the entire visible range has a bandwidth in frequency of about 300 terahertz. So what is the coherence time of this source? 1 over this, which is 3 femtoseconds. So if you take this lamp and interfere it with itself, at 0 delay, maybe you'll see an interference. You could see a dark fringe, a bright fringe. Then you make a delay of 3 femtoseconds. Now 3 femtoseconds is about just one wavelength, one optical wavelength, almost. Then it's gone. Why? Well, because this delay, what you need is a phase delay. In order to see an interference, you need to have a phase delay. But a phase is related to frequency. A phase is not really related to delay. In order to know how much phase you introduced, you need to know what frequency it was. I'll make a microsecond delay. How much is this in phase? Well, it depends on the frequency. For a slow frequency, it will be a small phase. For a large frequency, it will be a large phase. Because the phase is omega times tau. Now, if you don't know omega, then you don't know the phase. And that means that it could be for some frequencies constructive, for other frequencies destructive. And if you have both of them in your source, then they average out and you see nothing. You don't see the interference. So that has, this loss of coherence has to do with loss of knowledge. I don't know the frequency of my laser. Has to do with a phase difference. This is, so, you know, delta phi equals what? Equals omega times tau. If you know omega, then you're fine. If you don't know omega, well, you need to be careful. So for short taus, it doesn't really matter. If tau is short enough, then this is approximately 0 anyhow. But then you make tau longer and longer. At some point it becomes pi. Well, that's still probably okay, because as long as the frequency... So the question is, if I make a delay that is sufficient to do a pi, will I see an interference or not? The answer is usually yes, unless your bandwidth is so wide that you could also have 2 pi at the same time. If you have frequency, so if you have a frequency and also double that frequency, then you cannot even make a pi. Because once you do something that looks like a pi for one frequency, is actually 2 pi for the other one. So in order to know, to control interferences, you need to somehow know the phase. And that has to do with what we just did. So now, and then let's ask ourselves, now what about, so that was a discussion in time and we could understand things, and the question is, you know what, let's call this phi, and this let's call delta phi, the uncertainty of the phase phi, and that is the uncertainty of the frequency times tau. So if the time is small, then I can suffer a lot of uncertainty in the frequency. But once the time is large, then my ability to resolve the interference requires knowledge. So from here you can see why the uncertainty of the frequency times tau must be smaller, or for, I don't know, something of the order of pi. Let's call this. So this is to observe interference. To observe any interference, I need, this is a requirement. Okay. Now I can say the same thing in space. What do I mean? I can ask, so coming back to my source, so now here I have this is my neon lamp. Now I can ask, I was asking what's the correlation between the field now and the field later at the same point in space. Now we can ask, okay, what is the correlation between the field at the same time at two different locations in space? It's basically the same question. So I can ask, so I have, as we said, E of R and T. And what we now so far discussed was gamma of tau, which was E. Well, we understand. I don't want to write it again. But now I can. So we had before, so this gamma of delta T, or you know what? I had to do with the average of E of T, E of T plus delta T. Yeah. And star, average. Now I have a field here. Now I can ask myself what is, so I can talk about gamma. I want to say of delta R. Now I can define this as being the field at position R1 times the field star at position R2. Ensemble average, same thing.
It's the same wave travels another distance?
That's a good question. So the answer is...
It's the same like adding
no.
time.
I just want... So no, it's not. Because now we are in 3 dimensions. We're in more dimensions. So let's say that I'm talking about what it is
So
here.
you take a sphere
and
you put
here.
2 points on the sphere?
Not necessarily on a sphere, but I'm looking at 2 positions in space and asking myself what's the correlation between them. Now, before we go into this, clearly when those 2 points are very close, they will be correlated. Definitely if it's the same point, if I'm looking at distance 0, they will be perfect correlation, because what it will be, it's the same thing, will be the total intensity. So, of course, at 0 distance, there is a perfect correlation, because the field to itself is always correlated. But when you start looking at distances, maybe the correlation will decay. Let me just show you first how we can observe this in an experiment. So now I want to look at this is the point, I don't know, R1, and this is the point R2.
Yeah,
And then there is this source, and I want to look at the correlation between those 2 points. Yes?
and they are not necessarily in the same plane. They can be anywhere.
They could be anywhere, but let's, for simplicity, at least for now, let's put them at the same plane. So now I'll give you an experiment, okay? So I have a source. Then what do? I want to measure the correlation between those 2 points. And I put 2 slits. Small slits. One at location R1 and the other one at location R2. And then, you know what happens here? This is like thinking of the 2 slits experiment. So this is a source of, so here there's whatever field there is, but here there's a source of some spherical wave emitted from here, and here there's a source of another spherical wave emitted from there, and those 2 waves would interfere. Now if we want to make things easier, we will put here a lens, and this double slit case here, and then what we will have, those 2 will become 2 plane waves. This plane wave is emitted from this source, so we have this plane wave, and this one is emitted from the other one, so we have this one. And here we'll have, this is, you know, I should maybe draw it in 2 different colors. So let's make this one red, and it will generate this kind of plane wave, and the other one is now make it blue, and it generates this. And what will we see? We'll see, and I'll put my and I'll put my I don't know, screen somewhere. Suppose now that I put it here. Then here I see constructive interference. And here where the phase is pi, I'll see destructive interference. And here again, wherever the phase becomes constructive again, it will be constructive. So what will we see? Well, we'll see fringes, just as we do with a 2-slit experiment. But this requires, now the question is, well, what happens to those fringes? Well, now that depends whether this is bright and this is dark, or the other way around. What governs this? What governs this is the phase difference between those 2 points. Do those 2, assuming for now that they have, on average, they have the same intensity. Okay, of course, if one of them doesn't operate at all, then you won't see fringes. I mean, if the intensity of one could be 0, there would be no fringes. But another thing that would happen is if the relative, that's more important, if the relative phase between those 2 points is not stable, sorry, if the relative phase between them is 0, let's say that I have here a bright fringe and here dark. If the relative phase between those 2 points becomes pi, then of course every bright fringe becomes dark and every dark fringe becomes bright. So those fringes, they're always there. But where they are depends on the relative phase. Now if those 2 points have a stable relative phase, meaning that this, the fact that you know this, see, this is what happens, what's written here. What's the relative phase and amplitude, but specifically the important one is the phase. This depends on the phase difference between those 2 points. If this phase difference is stable, I don't care what it is, just that it's stable, that I know it doesn't change in time or from one or within the ensemble, then I'll see a steady interference pattern. But if not, it will wash out. Because the fringes will be moving too fast. So, I think this can go. Yep. So now, we can, and okay, okay, yeah, well, we should stop, but so we have this. Again, let's assume that I have a wave that I know perfectly. Let's take for a plane wave. What is this? Well, for a plane wave, we know that the field of R at any place is E to the I k dot R. So if I write this for a plane wave, this is just e to the I k R1 minus R2. And this, if I ask myself, okay, so what is this absolute value? So it is a function of the difference of R1 minus R2, and it's a constant. Indeed, for a plane wave has perfect phase correlation between any 2 points on it. If you know, I'll tell you this point is here and this point is there. You measure the distance between them, and you know exactly how much phase is acquired when the field moves. Now, it doesn't have to be a plane wave, of course. It could also be a spherical wave. It must be a wave that you know. Or, in other words, now a plane wave is this, right? But, of course, if I take a lens, I can make this plane wave into a spherical wave that converges to a point. And then, or maybe if I have a point source. So a spherical wave will also have a perfect spatial coherence. And then So what I want to tell you is that really that spatial coherence is related to this width of the source. Now, specifically here, this lamp, this is why a laser is spatially coherent, and a lamp is not. Because a laser can be focused to a point, and the lamp cannot. Why? Because, oh, by the way, so does the sun. The sun cannot be focused to a point. Why? Because there are different points on the sun that are emitted randomly. Nobody knows what the relative phase of 2 points on the sun going to be. There is no relation between them. And therefore, 2 different points on the sun do not interfere. Well, it's not that they don't interfere. Of course, they do interfere. But this interference is unstable, and therefore, on average, you don't see anything. This is a major thing. So, for example, you know, if I have here a source, you know, it's a bulb. And now what do? I'll just put here a lens and look at the and I look at the so because those different points are uncorrelated with each other, there's no stable phase between them, then what I want to say is, now suppose that now I'll take a lens and ask myself, okay, so in this distance would be the focal distance of the lens. Why am I saying this? Well, because all those, and we assume this is it's not a thick thing. I mean, this is basically a two-dimensional thing sitting here. It's a thin source, and then, you know, I can ask myself, okay, so what's the relation between the spatial width of the source and the angular width here? So now let's see. I have here a point source. What does it do? It emits light like this. And then this light is emitted that way at this angle. And then there's a source here in the center. This one is emitting light in this direction. Now, all of them are in the focal plane of this lens. So they are all generating plane waves. But there is an angular divergence to this. Why? Because this thing has a size, a finite size. So you can do this by saying, look, I can ask what is the relation between what happens on this focal plane to the other focal plane of the lens, and you know that there's a Fourier transform relation from one to the other. So that if I have here the spatial dimension here is related to the k vector dimension here. But you can also see that, you know, this is delta theta. This angle delta theta is related to basically the size, this delta x, the size of your source. And so the divergence of plane waves that you have has to do with delta x basically divided by the focus. Remember this, we'll discuss this soon because it will be related to Hunbury, Brown, and Twiss, which we will mention immediately after the break that we should have taken some while ago, but maybe better now than never. So yeah, and then I'll mention the relation to k vectors and Fourier in a moment. Well, basically because this is, you know, k is just the direction times 2 pi of lambda over lambda times the direction, and this is where the angles are. So when I talk about the k vector, or when I talk about the angles, it's basically the same thing up to a factor, which is wavelength dependent, but okay. So Actually, now we are ready to understand the Hanbury-Brown twist experiment. Because, well, no, let's think about what happens when we, when we image. If we want, I told you we can measure the angular divergence of the sun. Well, that's easy, of course. Well, I want to measure the angular divergence of the sun, and I don't know exactly where it is. So suppose that I'm not sure about the distance to the sun. So well, what does our eye do when we look at the sun? Well, then what we have is we have here, I don't know, there's the sun, and then every point here on the sun is uncorrelated. There's no correlation between all those points. And then, of course, each one of those points is generating I'm sitting here. So somewhere here, it's very far, I'm trying to make, I have my lens. It could be the lens of my eye, or it could be the lens of, I don't know. If we take, if we take a lens and if you want to burn something, so you take a lens and you put it exactly at focal distance so that you have a good focus of the sun on whatever it is that you're trying to burn. And that means that you're exactly at f focus distance. Why? Because then you refocus the light, and what do you see? You see an image of the sun. Now it's a little bit confusing because at the distance f you're supposed to see the Fourier transform. How do you see an image? The answer is it has to do with the fact that the sun is not just far, it's also very big. So, but in any case, let's think of the following. There's every point here emits a plane wave. So there's a plane wave coming from here. No, it doesn't emit a plane wave, sorry. It emits a spherical wave, of course. But let's put things in perspective. This is emitted to all directions from the sun. I'm sitting here at 150 million kilometers away with a lens like this. Okay? So how on earth am I going to tell the difference between this spherical wave from 150 million kilometers away to a plane wave? I will not. There is no actual difference. I mean, if we ask ourselves what is the phase curvature of this, so I can say that, look, there's this point of the sun, and then there's everything that happens on the way, there's a triple dot like this, but eventually what I see is a plane wave coming from that direction. So this is the direction, and there's a plane wave coming from here. And what this plane wave will do, it will focus to this point. On the other hand, there's another spot here. It goes along this line. It also starts, of course, as a spherical wave. But after 150 kilometers away, there's no way to tell that from a plane wave. So I have here something that looks like a plane wave. It will focus here, right? And here, and all the other points will be here, and what I'll have here is an image of the sun. And as you know, the image of something that is very far forms at the focus. You know, something that is at infinity has the image at the focus. Now, of course, this is not at infinity, but 150 million kilometers is sufficiently infinity compared to the focus of my lens. So, indeed, the exact location of the image is not exactly at f, but it's a tiny bit afterwards. But this tiny bit, we can calculate how much it is, and it's much less than a micron. So, so here we see the image of something that is very, very far, because this is r going to infinity. Now, I want to ask, and what about the angular divergence? Well, that's easy. Because what is the angular divergence? Here it is. This is what is the different angle from different points on the star. What's the angle? And that is related to the size of the image and the focus. So this delta theta, which is the angular divergence of the sun, has to do, this is the same, and it's related also to this distance, to this size, which is, say, delta x. So delta theta is just delta x over f. Now this was, what we did here was geometric. Now there's a question, okay, so can I resolve this or can't I? Now it has to do with the fact that, okay, well, yeah, this works, but why can I see this for the sun? Well, because the sun is big. Now, those points, are they really points? No, of course they're not. They're actually diffraction limited. You know, the lens has an aperture, and this aperture dictates the smallest what is the spot that you can see at the back focal plane. Have you all taken optics at some point? Do you know what the diffraction limit is? Yeah, good. So if I have, if I have just a single plane wave, I have perfect plane wave, truly a perfect plane wave. So if I have e to the I k dot r, this is a plane wave hitting a lens, where this is the perfect k. Then because of the finite size of the lens, the fact that the lens has an aperture d, we will see here a spot which is non-zero. It has, let's call this one not delta theta with like this. Let's call it delta theta, large delta theta. Why? Because I want to preserve the small deltas to the diffraction limit. So here there's going to be a delta x, which is related to the wavelength times the focus divided by the aperture. And there is 1.22 or 2.44, but all those are just prefactors and tell me they depend on this form of the lens. So this is the diffraction limit. That means if you have a single plane wave, you're not going to see here a point. You're going to see a spot. A spot has a limit. Now, look, what did I tell you? That the angular divergence is related to the size of the image divided by the focus. Now, there's a diffraction limit to this. What is the smallest angle I can resolve? Delta theta, which is the diffraction limit. The diffraction limit of resolving two points that are very close. Well, that is, of course, delta x diffraction over f, which is just lambda over d. So if I want to resolve two plane waves that have a very small angle between them, and assuming that the wavelength is fixed, there's nothing I can do about the wavelength of the source. I have to make my aperture wide enough. So, and this is the standard thing for a telescope. If I want, so for the sun, that's easy because the sun is big enough and the angles are wide enough, and even a small lens will do. Even our eye is has sufficient width to resolve this. Now, if we go back to Hunbury, Brown, and Twist, they wanted to do this, but for a star that is 8 light years away. And they wanted to do this in radio. So then you need a huge telescope. I mean, they could calculate how wide, they didn't really know, they wanted to measure. But they could estimate what would be the size of the telescope that they would need if Sirius that they were looking at had the size of the sun, or 10 times the sun, or 100 times the sun. And it turned out that they would need a telescope with several hundred meters of, and they didn't have such a large antenna then at the 50s, and honestly today we don't have that either. So what could they do? One thing would be what we do now, which is called synthetic aperture. We could have several telescopes at small ones at different locations, but if we could measure the field, something that you can do in radio, remember, in radio you can actually measure the field. If you could measure the field and know perfectly the distances and the different delays of the different locations, so that you can add them coherently to know, then you could actually, this is what the Event Horizon Telescope does. It looks at the black hole, which is not several light years away, but several million light years away. And it can image it. How? By actually coherently measuring the radio frequency field at each of the telescopes, having a perfectly timed clock in all of them, such that they can combine those independent fields to a complete waveform, making the Earth your aperture. It's just like how we make a big antenna, a big radar antenna from many small radar antennas. You know, long ago radars had antennas that looked like big dishes with a single emitter in the center. Now they don't anymore. They just look like a flat screen. What is it? It's a flat screen of many emitters, small emitters. But they time them in phase in order to generate a plane wave. Previously, the way to make a plane wave was to take a point source and have a spherical dish that will take this spherical wave and make it into a plane wave going that way. Now you can do that. You don't need that. You have many, many sources on the antenna, and you time them perfectly so that you phase them. If they're all in phase, they're making a plane wave going that way. If they have a relative phase, which is like this, so this one emits slightly later or before, then the whole plane wave can tilt. And then you can scan the direction without scanning the antenna. You don't actually need to move the antenna. You just need to change the relative phase between those all cases. These are cases where you are generating spatial coherence. either in a trivial way from a point source generating a plane wave, or in a non-trivial way by having many emitters that are exactly perfectly phased. But this is something that you can do in radio frequency, because in radio frequency we can both measure the field and, or at least with sufficiently low frequency and with perfect timing capabilities. These are things that we have now, but in the 15s they didn't. So they were treating the radio frequency that they were trying to measure very much like we treat light now. They couldn't. And still they wanted to do something. So now the question is, what could they do? So yeah, that's the diffraction limit of that. So now what they did was the following. They said, well, let's think about just only 2 points on that star. Okay, the 2 relatively far points. So I have, there is my star. There's a point here and a point there. As we said, what do? For me, they look like 2 plane waves. But what do 2 plane waves do? Well, 2 plane waves interfere. So there's a plane wave coming from that direction. So here it is. There's another plane wave coming from that direction. Here it is. And now I put my detectors. Okay. So here comes the point. What do I see here? Forget the fact. Let's assume for a moment that they have a perfectly stable relative phase. If they have a perfectly stable relative phase, what will I see here? Well, I'll see fringes, intensity, bright, dark, bright, dark, bright, dark. What is, and this distance? So we'll see. If this was coherent, we'll see fringes. And the distance from, let's say, bright from here to here, from the bright fringe to the dark fringe, is related to the angle difference, right? So, and in a moment you'll see where we're heading. So, okay, we'll calculate the relation between this to the angle in a moment. It's very simple. But we understand that, you know, the more the angle is, then the denser those fringes are. Now, but what happens in reality? In reality, we just told you there's no phase relation between those two. So those fringes, they exist, but they move. So if I look at a single detector, I see nothing. I can take a single detector, I can put it anywhere, I'll measure the same thing. I'll never see any. If I take a detector and I move it across, I see nothing. I mean, just a constant intensity. But now suppose that I'm taking 2 detectors. I'll put 1 detector here, measure the intensity. Well, I don't know what it will measure. It sometimes will be on a trough, and sometimes it will be, how do you say, איך אומרים C ושפל?
Peaks and troughs.
Peaks and troughs, right. So it will sometimes be on a peak and sometimes be on a trough, but it doesn't. So on average, it sees something. But now let's ask ourselves, what about the other detector? I have 2 of them. If both of them are sitting within the same fringe, then they both will be on a peak or on a trough together. So that means that the correlation between them will be perfect. They are seeing the same intensity. This intensity is fluctuating in time, but it's the same. Now you start making a distance between them. And this thing goes away. Now, and specifically, so if you have only two, exactly, if those are exactly 2 points, then you will see there at distance 0, they will see this, there will be perfect correlation. And then you'll come to a distance which is exactly this, the distance between a peak and a trough. And then they will be anti-correlated. Wherever one of them is bright, the other one is dark. And then you'll move on and you'll see recorrelation when you have exactly 2 pi. Now, of course, this is not just 2 points. There are many points here.
It also depends on the integration time.
Let's assume for now that our source is monochromatic, or that you filter out a sufficiently narrow bandwidth, so that delta lambda is well defined, sufficiently well defined. That the frequency, let's assume that this is
the frequency of the fringes which move.
Yes.
So if I have the integration time and I have
True. Okay. But the integration, but let's you know, you want, this source is not just far, it's also faint. So if you want to collect sufficient light, you'll have to integrate for a long enough time. This was the point that made those quantum guys' suffer. So they were integrating for a long time. So you're right. So the integration time was seconds or minutes. So it was, you were integrating for a long enough time to collect sufficient amounts of light. So then, no, I should be careful about this. Okay. There are 2 kinds of integration. One is the, let's call it the device integration time, the one that you cannot go below. Of course, you can integrate longer if you want. You can always decide that you integrate more. Now, the device limit, let's call it, I don't know, let's put it at a nanosecond. Okay, this is a reasonable assumption for electronic devices. Maybe it's a microsecond, but it doesn't really matter. Now, this tells you that you can follow things that change faster than a microsecond. Okay, so not faster, so slower than a microsecond. Now, so let's suppose that what they do is they indeed filter out something that over a microsecond, you are right in saying, look, this interference pattern is also wavelength dependent. If you have different frequencies, different wavelengths in your source, then each frequency will have a different interference pattern.
They can change very fast and then I can lose it on my detector.
Right. They could change even faster than, but for that, you filter out some of the, the frequency range.
And I look only on the wavelength?
Yes. So now, so we are assuming we took a specific wavelength of that source, and then, so now let's remind ourselves what happens. So I have here, so if I have here, then those are I want to say, yeah, so yeah, if I have, this is, say, so this is K1, and this is K2. And this is delta K. Now, of course, and this is the angle delta theta. So delta K, sorry, even not with this, just this delta k absolute value equals what? Equals the absolute value of k times delta theta, approximately, for small angles. Now we ask ourselves, and this phase, so delta x, so we ask ourselves, what is the distance that we need to do in order for this to become pi? So the phase delta phi equals what? Delta k times delta r. So that is the distance from here. This is exactly delta x. Or so if I ask myself, okay, so we can clearly, and this should be of order pi. So that means, I'll write it here, that delta x equals pi over delta k, which is pi over k times delta theta. So yeah, you need to know k, and k should be well defined, sufficiently narrow to define this. And then, okay, so now they said, look, what we're going to do, we are going to measure the intensity correlation as a function of distance. So what they were measuring is, they were saying, look, okay, there is, but of course the star doesn't have only 2 points, but many points. So what will you see? You will see there are, of course, many such fringe patterns, some from points that are close, so their separation is large. But the fastest fringe that there is related to the 2 points that are at the farthest points of the star. So what you will see is that you will see perfect correlation for 2 detectors that are sitting close to one another. You slowly make them apart, they lose correlation, and they will completely lose correlation on the order which relates to the fastest fringe, or to the farthest points, which relate to the width of the star. So what they were measuring are not field correlations, but intensity correlations. So they were looking at the intensity, or at R1, and the intensity at R2, and look at an average of this. If you want to think about this, this is like E R1 and T. That actually doesn't matter, squared, times E R2 and T squared. Average of this. Or, if I want to look at this a little bit further, I would write this as being E of R1, E star, R1, E of R2, E star of R2. Why do you make things so complicated? This is only they were looking at the intensity correlation. If you think about this, this is this delta x, and what they observed, and this is what? Now let's say something here. This is the average of I x1 intensity of x2 average. But that, if we look at this, we will see this. Something like this. Why? Well, because, well, you know, if you look at the intensity, the statistical average of this is larger than I1, I2 average. This is because if there is correlation, if there is no correlation between x1 and x2, then the average of the multiplication is just the multiplication of the averages. And if there is correlation, then this one will be bigger. And as you know, the fluctuation is the difference between that one and that one. So here, what we have, this is the intensity squared. The average intensity squared. Of course, both of them measure the same. So this is the level that you see here. But here there's a peak. And this width, delta x, is related to the width of the star that they wanted to measure. Now here comes the point that got the quantum physicists go nuts. If you calculate how many photons were absorbed during the short integration time, you know, that what they were doing was that they were measuring, of course, we just said, look, they had to integrate over a long time. Yes, they did. On the other hand, they had to look at sufficiently short. You know, those fringes, they fluctuate. At what time? Well, that depends, as you just said, on the bandwidth. Now, they didn't want to filter the bandwidth like crazy. So they filtered the bandwidth, the minimum that they had to, which had to do with the minimum the maximum bandwidth they could have on their detectors. So that means that they were operating at technical integration times that are as short as possible. Because you want to see things that are fluctuating, and you want to correlate between those two fluctuations. And then they were, in order to collect sufficient data, they were integrating this. They were calculating the intensity, you know, they were taking the time intensity here, time intensity here, multiply them, and now average for a long time so that you could look at the, and then the people from quantum physics said, what are you talking about? In your short integration time that you are doing, in this microsecond or nanosecond that you were looking at every point, there's no plane wave or anything. There's only a single photon. If you detect a photon here in this detector, how could you detect it there? There's only one at maximum. So it's going to be either in this detector or in this detector. So how are you talking about intensity correlation? How could there be? You're telling me that, look, when the intensity in this detector is high, the intensity in this detector is also high. So if we think about single photons, how could that be? There's a single photon. It is either here or there. And your intensity is so low that on average you have less than a photon per integration time. So how could you talk about intensity correlations when all you have is a single photon and it's either detected here or there? something is wrong with the experiment. I don't know what they're measuring. There's something, yeah. They don't understand physics. But first of all, there's one thing that you should know. If you're doing an experiment that could be understood classically, the classical explanation is better. So there's nothing wrong with the Hunbury, Brown, and Twiss experiment. And they did measure the angular width of that star that was there. I think it was Sirius, as far as I remember. But you could look it up and make sure and correct all the mistakes that I said during this lecture today. Here is the point. The main point is this. Weak light is not a single photon. And this seeming paradox is, in order to solve this, you really need to talk about the coherence of, what. So you really need to talk about quantum coherence. And what does it mean to discuss quantum coherence? So we will do this after we quantize the field and after we define the field operators. So we'll discuss this. But so right now I'm just showing you the paradox and telling you that well, we need to somehow solve this. The solution has to do with the fact that if I told you, if I take this, lamp, I'll just make it weaker and weaker and weaker by filtering out more and more and more light. Eventually, or I'll take a detector and I'll make it worse and worse and worse. So even in this light, it only makes a click once in a while. The fact that I have single clicks does not mean that I have single photons. I have single electrons. And weak light is never a single photon, even if you have single events. If you want to have a single photon source, you need to have a single atom or a single emitter that really emits a single photon. Now, and to know this, you'll need to do something. And of course, the star, Sirius, does not have only a single atom. And it's not a single emitter in any way, and it definitely emits a lot of photons. And that means that the probability, maybe the probability of detecting a photon is going down. And the probability of detecting 2 photons is going down. And the probability of detecting 3 photons is going down. But the ratio between those probabilities stays the same. So, okay. So it's never going to be a single photon source. A single photon source means that you can only detect 1 photon and there never are 2. But now what happens? Okay, the probability to detect a photon is sufficiently low so I can have clicks. But out of those single clicks, the number of those that are actually coming from 2 photons didn't change. It's the same. So the ratio, the fraction of 2 photon events or 3 photon events, all those fractions, they remain the same. The total probability, all total probabilities goes down. So that has to do with where things are coming from. But now, so now we can define first order coherence. We discussed coherence in space and discussed the coherence in time. So now we can say, well, first order coherence. Well, in the very general case, it's a function that depends on 2 points in space and 2 points in time. What is this? It is the correlation between the field in point 1, T1, and point 2, T2. And that's it. There's nothing else to define. So there's only one function. The ensemble average. And we discussed the consequences of having 2 points in time. Usually you either change one or the other. And you can talk about a field that is coherent in time or coherent in space or coherent in both. Coherent in time usually means that you have a single frequency. Coherent in space means that usually means that you have a single plane wave. And if you don't have a single plane wave, then you have a single spherical wave that could be transformed into a plane wave by a lens. Doesn't matter. You have a phase front that is well defined. And here you have a frequency that is well defined. So that's first order coherence. What about second order? Now it becomes, basically there are 4 points in space and in time. Now you could say, well, this gamma 2, that would depend on R1 to R4 and T1 to T4. And it would look like and then you can make, okay, I'll write it first and then you can make the generalization. That would be the average of what? E of R1 T1, E of R2 T2, E star of R3 T3, and E star of R4 T4 on average. Things become too long on this board. Now you can see how quickly this can go crazy if I go to nth order. So that's a 2-point correlation. Or sorry, that's probably 1-point correlation. That would be 2-point correlation. So I'm correlating, I'm looking at the, now what are we asking here? Now, so this is a general thing. Now honestly, nobody will look at this really general function. This intensity correlation is a very special case of this, where R1 equals R2 and T1 equals T2. Sorry, no, wrong. Where R1 equals R3, T1 equals T3. So the intensity correlation is when R1 T1 equals R3 T3, and the same goes for R2 T2 equal R4 T4. Because then you can immediately see that we have here E of T1 and then E. Let's immediately take this E star of T1 times E of T3, E star of T3, and this is indeed the intensity correlation. I1, I2 average.
It's supposed to be 2 and 2.
What?
It's supposed to be 2, not 3.
Ah, you're right, you're right, you're right. Thank you. But, by the way, I can ask what is the correlation of the field squared? That's not the same. So that's a special case. Now, people sometimes look at intensity correlation as being the second degree of coherence, the second order coherence. When people say I'm measuring second order coherence, they mean I measure intensity correlation. But as you just saw, this is the definition. It's very general. You could have other forms. For example, you could have second order field correlation being, let's take another case, which is just and here we'll stop. Yeah, we should. So for example, if I take the case, another special case, and that would be E squared coherence. It is of importance, but and that is indeed where R1 equals R2, or sorry, R1 T1 equals R2 T2, and R3 T3 equals R4 T4. Let's see. Then we will have, and then we will have this gamma of, we can still have this delta R and delta T. That would be the average of E squared of T1 times E squared, E star squared of T2. Well, yeah, in this case, when we wrote 3, then it remains 3. But,
1 and 2 are the sources, and 3 and 4 are the one that I measure?
Not necessarily. Those are the 2 points. I'm looking at the correlations between the fields at 2 points. Now, when I'm looking at second order, then there are 4 points involved. Originally, we were looking at the correlation between this point in space-time and this point in space-time. Same time, different locations. Or same location, different times.
And now I have 2 points.
So now I have 2 points.
Yes.
So now there are 2 points you start with and 2 points that you end with. And you're looking at the correlation between them. So now, so out of this you can form all kinds of crazy forms. You don't always know what their meaning would be, but there are 2 cases that really do have a meaning. One is the case of intensity correlation. I just showed you what it has to do with. The other one is the case of correlation of E squared. This has to do with nonlinear optics or nonlinear events. I'm not going to say much about it, except the fact that it does look interesting just as well.
E squared is the intensity of the first one?
No.
It's supposed to be E times E.
This is complex.
It's supposed to be E times
E, remember, E is a complex number. This is the, that's the amplitude. It's an amplitude and a phase.
Yes.
So here, there's the amplitude and the phase. So this is a complex number.
Mm-hmm.
This is a different complex number. The result of this is complex, basically. And then you could look at the real part of it or the imaginary part of it. But this is a complex thing. Whereas the intensity correlation, where was it? That's...
Yeah, because E times E star.
Yes, we're looking only at... OK. So I think now is a good time to stop. Quantization next week, I promise. So now you've seen first order coherence. You saw the Hanbury-Brown and Twist paradox. We didn't solve it yet, but you got a feel to where it is coming from. It has to do with the fact that weak light is not, and it never will be, a single photon light. So this assumption that is very common to think that, well, you know, I reduce the intensity of the light, and if it's low enough, then I have single photons. No, you never do. You never have single photons unless you really isolate a single emitter, single quantum emitter, and then maybe you can talk about single photons. Because this emitter cannot emit two. But if you do have a possibility of two emitters, you'll always have a possibility of two photons. So a photon is not a clique. And we'll see more of this next week because we will start with the semi-classical photodetection. And then we'll quantize the field. Okay. Bye-bye.